Today we're going to talk about nucleotides, another class of compounds that are needed for life. And the nucleotides are what make up DNA and RNA. The reason for this lecture on this series in abiogenesis, again, many of you may have seen this, bear with me in case somebody's just joining us for the first time. Dave Farina posted a video entitled Elucidating the Agenda of James Tour Defense of Abiogenesis. You can see in the description box below, just right down below, you can link to his video. After I watched the video, I was confused about almost every slide and every statement that Dave Farina presented. There were numerous gross scientific inaccuracies in his claims, in my opinion. Since others might be likewise confused, I'll use the Farina video with timestamps as a launch point for the series of these lectures, because many people probably believe like Dave. So let me help out lots of people here. I'm thankful to Dave that he attempts to teach a layperson about scientific topics on his YouTube channel, which is Professor Dave Explains his YouTube channel. That's a commendable endeavor. I therefore seek no contest with Dave Farina, only to bring clarity. I don't want any contest with him. Other synthetic chemists, I invite you, come on in here and point out where I'm incorrect. You know, I'll probably say a lot of little wrong things. I mean, anytime I give a seminar, anytime I give a class, lots of things that I can say that might be wrong. But if I've said anything major that's wrong, I invite critique from my synthetic chemist colleagues and students studying synthetic chemistry and those studying origin of life. Point it out. But if you do me the favor of giving me an article on it too to help me to really know, I'll appreciate that. All right, nucleosides and nucleotides. A ribonucleoside is a compound formed between furanose form of D-ribose and a heterocyclic compound. The deoxynucleoside is related but lacks an OH at C2'. All right, so you have this sugar. So in order to make DNA and RNA, you have to first solve the carbohydrate problem. You have to make carbohydrates. And there was one clever synthesis that John Sutherland has done, and we'll talk about that, where he actually built the carbohydrate around the base. So you have a base hooked up to a carbohydrate. But again, carbohydrate synthesis is really hard. And remember all the different enantiomers you can have. So this is a stereogenic center. There's one, there's one, there's one. So you have 4 stereogenic centers in there, so you have 2 to the 4th possible isomers. It's hard. In all commercial syntheses, these are purchased. You buy these from the manufacturers. So when people are doing automated synthesis in a machine that looks so easy, yeah, because you bought this from a commercial manufacturer. And the commercial manufacturer didn't make it. They didn't synthesize it. They didn't synthesize the sugar. They didn't synthesize the base. They extracted the base already hooked up to the sugar, already with the phosphate on there, and they put it in a bottle and sell it. So all the building blocks of the building blocks you get from nature anyway now. They don't build this up from ground zero. When there's an OH here, this is for RNA. When it's devoid of that, that's for deoxyribonucleoside. That's the deoxy, meaning without oxygen. That's for making DNA. So you see the relation. DNA and RNA are similar. They have a base, and these bases can vary. They have some of the common bases, some unique. Nucleosides and nucleotides. The bases that occur most frequently are the pyrimidine and purine bases. Here's the pyrimidine bases. They have this general setup. Here's the purine bases. They have this general setup. There's these 2 purine bases, these 3 pyrimidine bases. This one is used solely by RNA. This one is used solely by DNA. And when I say solely, I mean predominantly. All right, nucleosides and nucleotides. A nucleotide, the A' phosphorylated nucleoside. So you have a phosphate out here, and that now makes the nucleotide. So nucleoside is devoid of the phosphate, nucleotide will have the phosphate, and so this is going to be the one for RNA because it has the two hydroxyls here, and the same for RNA here. Sometimes it'll have one phosphate. You could condense 3 phosphates. Ribonucleotides are derived from the monosaccharide ribose. Deoxyribonucleotides are derived from the 2-deoxyribose. So when you have DNA, you're devoid of that oxygen, which would make it much more stable. All right, nomenclature. So you can have these different bases. This is the nucleoside. This is the nucleotide with the 5' monophosphate on there. And this is the abbreviation for them. And if you have a D, that means deoxy for the one that's for DNA. All right, the structure of DNA and RNA. Nucleic acids are polymers of nucleotides. So you take those nucleotides, you string them together, you get nucleic acids. That's what DNA or RNA. Deoxyribonucleic acid, DNA, is a polymer of deoxyribonucleotides. The monomeric units of the DNA polymer are called residues. Ribonucleic acid is structurally similar to DNA but employs ribose, not the deoxyribose. All right, so here is now DNA because you don't have that extra hydroxyl group here. And you have this phosphate is going to be hooked to, so the phosphate is this linker between the sugars, and the sugars have the base. These bases, A, T, C, or G in DNA. You have the 5' end and the 3' end. All right, so the structural features of DNA, you have 2 right-handed helical polynucleotide chains run in opposite directions around a common axis. The sugars and phosphates are rich in hydroxyl groups and charges that are located on the outside of the helix and interact with water. The chains are held together by hydrogen bonds, A to T and C to G, referred to as Watson-Crick base pairs after the 2 gentlemen that deciphered for the first time the DNA structure. Structural features of DNA. The planes of successive complementary bases are stacked one on top of the other and perpendicular to the axis of the helix. We'll see that. A major groove and a minor groove are present in the double helix. Proteins and other macromolecules interact with these molecules. There is no restriction on the sequence of bases. However, the base pairing must be complementary. All right, so you have to have this complementary base pairing. So in other words, you have this helix, you have a major groove, and you have a minor groove, and this is the stick version, this is the van der Waals version, this is the stick version. And then if you look from the top, this is the viewer's eye, you look from the top, this is what you're going to see. It's going to look like this. And the phosphate groups are pointing outward. Those are very hydrophilic, those interact with water. And then there's hydrogen bonding across these flat bases in there. And so you see this basing between, for example, the C and the G base pairing, which has 3 hydrogen bonds, and the T and the A base pairing that have 2 hydrogen bonds. And these are these hydrogen bond stacks that are occurring. This is, again, looking down through the top and seeing these hydrogen bonds. All right, and so these then form helices, and they're double-stranded. And one runs one way, one runs the other way, and so they're complementary, which is very convenient. And these then start unwinding to start allowing proteins to make RNA from this DNA template. And then the proteins will start, then the RNA will then start synthesizing the proteins that are needed for whatever function we need in our body. That's the way this thing works. Isn't that remarkable? It's really remarkable. All right, so some say
Jim is constantly talking about how we don't know how to make the 4 classes of biomolecules, which are nucleic acids, proteins, carbohydrates, and lipids. This is ridiculous. Nucleic acid synthesis and protein synthesis are utterly trivial. It's so easy to do that we even figured out how to make machines that do it for us. We type in the sequence we want on a computer, let the machine run, and we can get a DNA strand of any sequence of nucleotides we want, or a protein of any sequence of amino acids we want.
So I don't think that this is a DNA synthesizer. I don't think so. But in any case, maybe it is. I don't know. But nucleic acids, proteins, these are utterly trivial to make, he says. Well, let's see how utterly trivial they are to make. And remember, just making them today has nothing to do with how they would have been made in a prebiotic Earth. all the building blocks of the building blocks, the nucleic acids, all of the nucleotides are isolated from natural sources today. If you had to synthesize those, even using modern synthetic methods, it wouldn't be easy. Using prebiotic methods, it's impossible to do it in anything near a homochiral form. More statements by some people. Some people say this.
Any biomolecule is easy to synthesize.
Any biomolecule is easy to synthesize. Huh? And furthermore,
Jim knows this. He's a synthetic chemist. What he probably means is that we haven't seen these biomacromolecules form spontaneously outside of a biological system. But that's not what he says. He does not make the distinction, and this seems deliberate on his part.
And this seems to be deliberate on his part. I've never even seen them form spontaneously in a biological system. But nothing forms spontaneously. There's a lot of chemistry that goes on in this. No, I didn't know that, and neither does any other synthetic chemist. It's difficult for chemists to make most macromolecules, and to date, impossible when restricted to prebiotic chemicals. And much harder for the prebiotic Earth, where the Earth could not buy the nucleotides, that's the nucleobase, the ribose, and the phosphate, all hooked together in homochiral form. And no chemist in her right mind would support the claim that any biomolecule is easy to synthesize. And remember, you got to go out on that barren Earth and scrounge up the chemicals to do something like this. Hard to think about that. All right, so how is solid phase synthesis done? Well, you take your base and so you have to first hook this on to the glass bead. Let's see, we're just hooking on to the glass bead. It's already hooked on. So we'll start right here. So here's a base hooked onto a glass bead. The glass bead is a controlled pour glass bead. So this glass bead you hook on, and you have a DMT group which has to be protected. Why'd you have to protect it? Because or else that free hydroxyl would have hooked onto the glass bead as well. So you had to keep that protected. So you buy the base, the nucleotide, with a DMT group on there. That's what goes in the machine. It looks easy because all the synthesis was, all this coupling was done, all the isolation from the natural source, and then the coupling was done before you ever bought it to put it in your machine. And then you deblock it, you pull off that DMT group, and then you bring in this phosphoramidite where you have this activated system, the DMT protected. That hydroxyl group is then going to attack that phosphorus, and you're going to lose that amine, and so you get to this phosphate precursor group, and that's what remains in there protected. And then what you have to do is you have to see that not all of these are going to be coupled on. And that's why you do it by solid phase. And some of them never grew. And so you put an irreversible capping agent on that, and so that will never grow again. You have to do all this solid phase so you can wash out all the impurities and cap these things. And then what do? Then what you do is you take this molecule and so you've removed out the capped ones. The capped ones are no longer going to grow. They're still stuck on the bead, but they're never going to grow. And then you do an oxidation that removes this nitrile, and that will give you, it keeps the nitrile, but it oxidizes the phosphorus. And so now you have the phosphate group here, but you still keep this nitrile, which you're going to remove at the end of the synthesis, and then you go over it again. So it has all of these steps are involved. To just add on 1 unit, just to add on 1 unit, you have to do all of these steps. So solid phase steps, DNA synthesis, the starting materials come from biological and synthetic sources. So the base hooked onto the deoxyribonucleic acid comes from a natural source. And then you put on this synthetically prepared phosphoramidite, and it's used to protect the 3' hydroxyl. And then you put this DMT group on here to protect the 5' hydroxyl. And these each come with a base, but the base likewise has to be protected. So if you have any one of these bases, they're going to have to be protected. So you see this acylation here that takes place on these free bases. So the base also has to be protected. You can't just use the free base here. That's hooked on there as well. All of this you buy, and it's all been partially isolated from natural sources, and then selectively protected. Because you have to have certain groups blocked or else they would interrupt the synthesis. That's why we don't know if this was ever done in a prebiotic Earth. Now here's what the company that does DNA synthesis for a living writes on what's involved in each one of these cycles. Deblocking. 3' to 5' nucleotide addition requires initial removal of the DMT protecting group on the 5' of the receiving oligo. This is accomplished by treating the oligo with specialized deblocking reagent, which leaves the oligo with a free 5' hydroxyl group that can then react with the next nucleotide. This step is also known as detritylation or deprotection. Step 2, after deblocking, then you have to bring in this phosphoramidite and do the coupling, and then you have to do the capping, and you have to do the washing, and you go through this over and over again, and then you have to do the oxidation. These are all involved. So just because you can program it in a machine, I mean, it's still very involved. There's a lot of chemistry behind it. It's not trivial. Not trivial at all. Tell that company it's trivial and see what they say. Then, after the repeated recycling, you have to have the final processing and then desalting. So you have to knock off all these protecting groups that were on there, pull it off the glass bead, and then it's not ready yet. It has to go into purification. So it goes into there's these two different types of purification. There's this polyacrylamide gel electrophoresis, PAGE, and there's high-performance liquid chromatography. So you have two different types of purification that have to be used here, that can be used on this, because you have to get away from all those capped ones that never grew. This is hard to do. Yeah, you can program it in. What are the suggested prebiotic routes to nucleotides when solid-phase synthesis from a functionalized glass bead is unavailable? How do you do this in a prebiotically relevant way? And the base and the sugar cannot be isolated from biological source because biology is non-existent on a prebiotic Earth. It's prebiology, that's why it's prebiotic. How is it done? This is what people foresee might have happened, and so they map out a lot of these synthesis, and a lot of these are unknown steps. When you see all these double arrows, these are all unknown how this might have occurred. But it's one of these syntheses in here that we're going to get to where Sutherland has done this without going through the sugar. All right, he builds the sugar around it. But a lot of these steps, we're going to see, are these steps really realistic? This is what we're going to look at. But this is presumed prebiotic nucleobase, nucleotides, DNA, and RNA, and then a cell. So a lot of this is unknown steps, and a lot of these people have done in the labs. All of this is racemic. A lot of this has not even relative stereochemical control. None of this has absolute stereochemical control. So in that case, it's prebiotically irrelevant, every bit of it. All right, so here's the Sutherland synthesis. So he starts from these small molecules, he goes around, and that's this section here. It includes some of this here. So it's this section here, mapped out. And with this section here, he goes to this intermediate. So here you have your RNA that has a phosphate, it has a free hydroxyl, and it has its pyrimidine base on here. So he made this without pre-making the sugar. Very clever way to have done this and saying, well, maybe this is how Earth did it. Well, let's see, is this really relevant? Could Earth have done this? Prebiotic Earth? We've seen this synthesis before, but this was one of the steps that he needed in this synthesis. And he made the triol here because he needed this triol somewhere in here. He needed this triol. So here's the oxidized triol. So you can see this because he's got to put an aldehyde on this end. So does this sound like something that can be done easily on a prebiotic Earth? Dihydroxyacetone. Where he got that, I'm not sure, but I'm sure there was, he went through that. Not easy to make. Dihydroxyacetone, but I'm sure the one he's using in his synthesis, he bought it. And sodium hydrogen phosphate were dissolved in water, and the resultant solution was degassed for 15 minutes. Degassed. How do you do degassing on a prebiotic earth? How do you degas on a prebiotic earth? Nobody knows. Sodium hydrogen sulfide, 60 milligrams, was added and the solution turned yellow. When the sodium hydrogen sulfide was dissolved completely, the pH was adjusted to 7 using degassed sodium hydroxide hydrochloric acid. How convenient is that? He brings it to pH 7 using degassed sodium hydroxide and HCl to adjust it just to pH 7. How do you do that on a prebiotic earth? Hard. The solution was then transferred to a quartz tube. Where are you going to find that on a prebiotic earth? You're not. Quartz tube containing copper cyanide and immediately sealed, whereupon a black precipitate formed. How are you going to immediately seal a system on a prebiotic earth? The tube was then placed in a rayonette reactor and then irradiated for 6 hours. A rayonette reactor is a box that has a lot of UV lights in it, and you set your reaction mixture in there and you use a quartz tube because it doesn't absorb UV light. And after this time, an aliquot is removed and checked. And so remember, this is what he wants to make. This is an authentic spectrum using a compound that he bought. Here is what he made. All of these other peaks that you see in there, these are all exogenous peaks of something he doesn't want. That's why he did not use this. He just went out and bought it. He identifies this as a peak in a HPLC or in a GC, and he will never use it. He just goes on from there. If he puts it on a vacuum pump, he can pump off some of these volatile compounds. But where do you find a vacuum pump on Earth? How does that happen? You want to launch it into space? How's this going to happen? So the origin of life researchers' secret, relay synthesis over and over again to bypass low yields. So you take A and B and you get a series of compounds, AB1, AB2, AB3, AB4, AB5, all the way up to ABN. You see all of these compounds in a HPLC, but you only want this one. So you don't isolate it because it's too messy. It'd be too hard to isolate. So you synthetically make AB4 using modern synthetic methods and modern methods of purification, or you buy AB4, which is generally what they do, which is gotten from a natural source. In this case, they have the triol, which is glycerol, which you just buy for almost nothing. And then you take AB4 that you've purchased, that you said, oh, look, I made it by a prebiotic route. Well, you really didn't because you didn't carry that on. Yeah, it was a little blip, but it was unusable. But you expect prebiotic Earth to figure out how to use that? And you mix it with C, and you get AB4C, 1, 2, 3, 4, all the way up to AB4CN. And this is the one you want, for example, AB4C6. It's a little blip in a mixture of a lot of other blips in your spectrum. You don't use that, you buy it. You buy it. That's called a relay synthesis, and it's cheating. And they do it at every step. Most synthetic chemists don't even know that this is the game that's played in prebiotic chemistry. And they take that, they mix it with D, and they get a series of compounds. They don't carry that on, and they repeat that. So generally, this is what they'll do. They'll generally not carry it on. Then they purchase or synthetically prepare this, and they repeat this over and over again. Yeah. So all of that synthesis you saw, that's not real. When reading the precise protocols of Sutherland's suggested prebiotic-like precursors, one captures the high level of sophistication, expert synthetic prowess, and remarkable ingenuity of the researchers. Some reactions were conveniently run at room temperature, some at 60 degrees, others at 100 degrees, and then washed with ice-cold water, dried under vacuum. Often the molecules prepared by these supposed prebiotic routes were not used, but they had to be made more cleanly and in larger scale using purely synthetic methods and organic solvents such as Lawson's reagent and tetrahydrofuran to, quote, simplify the handling procedures, unquote. That's what they say. No, it's because you couldn't do it. Just-in-time and precise order of addition protocols were used over and over again. One sees precise pH adjustment through the syntheses, use of ion exchange resins, and separations from the reaction mixtures because proceeding without separations would have destroyed the carefully prepared products. So you put upon a prebiotic Earth, which has the inability to purify the way you do, and you say, well, somehow it carried along these impurities. I couldn't, but prebiotic Earth could. The prepared cyanoacetylene, copper 1, was suggested as a way to conveniently prepare and store for use when needed. Copper chloride was mixed with KCl, potassium chloride, to generate the Newland catalyst at 70 degrees centigrade. Then a separately generated source of acetylene gas was prepared from calcium carbide and water. I didn't even know calcium carbide is pre-biologically relevant. I thought calcium carbide is made by treating a carbon with a very high voltage and calcium oxide, and then you can get calcium carbide. I don't know if you think you had a pile of carbon and a pile of calcium carbide next to it and a lightning strike and you got calcium carbide, but okay, I'll give you that. If you take calcium carbide and you drip water on it, it will generate acetylene. But the acetylene just goes up in the air. But somehow he is bubbling that acetylene that he's generating into his reaction mixture. This gas was bubbled through the Newland catalyst to prepare an acrylonitrile, an unstable molecule that needs proper isolation and storage to inhibit its polymerization, which was then treated with potassium cyanide for 1 hour. Then 5 equivalents of ammonia as a 13-molar ammonium solution adjusted to pH 9 with sodium hydroxide to generate the desired aminopropionitrile. And I know you synthetic chemists are scratching your head like, is this prebiotically relevant? All of these reactions were executed in separate clean vessels and properly isolated prior to proceeding to the next step. This is just a sampling of the preparations that are difficult for even the most skilled synthetic chemist, preparing very simple precursors to a few of the many molecules within the building block class, and all of their precursors were racemic if they bore any possible stereoisomer. So what we're making here is not the building block. What we're not making here is not the building block of the building block. We are trying to make the building block of the building block of the building block. Racemic ribonucleotides, thus prepared as in the previous slide, would have never been shown to polymerize under these abiotic conditions. The RNA that he made there was racemic. It never would have polymerized under these conditions. It's said in that video, molecules aren't made just one time. That's true because they aren't made any time by this route. Not just one time, they're not made any time. Small molecules, synthesis, and you form your RNA nucleotide. How? How? When you're making a video like this, how do you just say synthesis? How? Show me. You got a reference on that? Do you have a reference on that? Has anybody done that in the lab using modern synthetic methods to take chemicals and make a ribose and hook this thing up to it? Has anybody ever done that? And then they polymerize. How do they polymerize? They don't just spontaneously polymerize because you got these 2 free hydroxyl groups. Those are going to compete. And how do you get these different bases? So you're going to mix all of these different ones with different bases? And why don't these free hydroxyl groups compete? Why doesn't this hydroxyl group compete? Why doesn't this amine compete? You haven't protected these. But somehow, on a prebiotic Earth, it didn't have to protect them. But in laboratories and in the machines, you have to protect them. And then once this is made, this is terribly unstable. This is RNA. That hydroxyl group right there just swings around, hits that phosphate, boom, that comes off. You say it doesn't matter if it depolymerizes. It doesn't matter. It'll just repolymerize. But with the same sequence? How does that happen? It just repolymerizes. And remember, not everything has an equilibrium constant of 1. A lot of these reactions have an equilibrium constant of 10 to the 4th or 10 to the 5th. They don't go back. It's 1628. Some have said
the fact that it degrades is irrelevant if it is constantly being formed as well, and even more irrelevant once self-replication came about, such that a mechanism is in place to continually build copies given the raw components.
The sequences are repeatedly reproduced through the random polymerizations, not when they're 10 to the 40th combinations. Also, biomolecules can self-replicate. Which biomolecules are known to self-replicate under prebiotic conditions? Can you tell me that? You got a reference on that? Which molecules self-replicate? RNA? All right, what else self-replicates? And we're going to see how efficient RNA self-replication is. We're going to see. But you know any other molecules that self-replicate? Because you throw around self-replication as if it's a phenomenon that just pops up. In 832 in that video, I claimed, because he was showing pictures of me from another video, I claimed that there would be no information in randomly assembled DNA.
There would be no inherent information in the DNA. But even if we gave them the DNA in the structure that they wanted, they wouldn't know how to put all the components together.
Where others have replied,
this is just nonsense. He is saying there is no information inherent in the DNA when DNA is inherently information because of the way genes code for proteins when expressed. Jim is way out of his element when it comes to informatics. Nature did not set out to generate a particular amino acid sequence. The process was completely random. Countless different sequences were generated. It was only when a protein ended up having some particular function by chance that its production was preferred statistically.
Selection does not exist on a prebiotic Earth. You can't just put oligonucleotides together in any sequence and have a viable DNA that encodes something. You have to have the right codons. So what happens is you have this DNA that has a certain sequence. And so what it will do, it will translate into RNA that has a particular sequence. And these particular sequences, these 3 unit sequences, are called codons that translate into the synthesis, which then builds the proteins. All right, so you have the RNA, and these prescribe which amino acid is going to go on there. If you just randomly hook these together, you don't have the codons to make these. In biology, DNA carries the code for how amino acids should be ordered. Transferring that code to RNA, which then builds the proteins. Nucleotides randomly hooked together to make DNA. There's no information there. You need the information coding. One needs to string them together in a way that carries codons in order for them to translate the information to RNA synthesis and then protein synthesis. These 3 unit sequences are called codons. That video addressed nothing about where the information coding came from. Why? Why not? Because there's no answer to that. That's why. The sequence of amino acids is essential for peptide synthesis to display function. You have to have the right sequence. How do the nucleotides know to hook up in a prescribed order to form the codons for the particular peptides? And again, this is somehow happening in the ocean. So here we are again doing a condensation reaction in water, I presume. Because which solvent are you going to use? Remember, in those machines, they use dry solvents. They don't have free water in there. Highly dried solvents. What are you using? What's the solvent here? What solvent was there on a prebiotic Earth besides water? Tell me about it. Remember, oil came from biology. That's where oil came. What solvent are you going to use for this? You're going to do condensation reactions in water? Some suggest
nature had no specific plan like chemists do. There was an element of selection coupled with self-replication, and all of the structures he is referencing simply weren't the ones that were selected. That's all there is to it.
All of the structures he is referencing simply weren't the ones that were selected. That's all there is to it. Yes, chemists can be selectors. Chemists can build things with great difficulty that might select something from a reaction mixture upon which it can react further. But chemists were not present on a prebiotic Earth. Chemists weren't there to do the selection like chemists do. What selector are these people talking about? Selection does not exist on a prebiotic Earth. There is nothing to do the selection, and there is no target to motivate a choice. Molecules have never been shown to move toward life. Molecules don't care about life. Organisms do. Molecules do not. They don't care about life. Selection does not exist on a prebiotic Earth. There is nothing to do selection, and there is no target to motivate a choice. Show me a reference on selectors that could have arisen on a prebiotic Earth. Show me a reference on that. Generally, selectors are far more complex than the things that they are selecting. So when you throw out this term, when anybody throws out this term selector, it is ridiculous. It has no basis on a prebiotic Earth. There is no selection being done prebiotically on a prebiotic Earth. RNA self-replication. Well, when you say that RNA can self-replicate, there's an example of a molecule that can self-replicate. Well, let's see how well it can. In general, RNA replication needs RNA polymerase or RNA replicase. Those are enzymes, as in viral RNA polymerases. However, in the RNA world explorations, researchers have made specially designed primed RNA that can replicate itself without exogenous enzymes. Gerald Joyce is one of the leaders in this field. But these self-replicating RNA enzymes are limited, far from a general application, and they have not duplicated a significant portion of themselves where further daughters could ensue. For example, a short RNA of 189 bases could replicate an 11-mer from primed template strands, so 6% of it. So only 6% of something that was set up to self-replicate could self-replicate. It had an error rate of 1.1% per nucleotide, which is a high error replication. It's a high error rate, very high. Remember, at 1.1%, remember we had to have all those washing out steps, and we had to put this through HPLC? You can't deal with an error rate like this. The largest it was able to replicate was a 14-mer, which is also too short for self-replication. The record is 20 bases long, but again, too short for further replication. So these ones that it replicated could never replicate anymore, and it didn't replicate the whole thing, only short segments, and these were primed, set up in a laboratory under pristine conditions. Obviously, all the component nucleotides were isolated from natural sources. This RNA that was made and all the things that were replicated, these nucleotides that were used were not made prebiotically. They were taken from nature to be used. Nobody knows how we got these in the first place. Just so that people might understand, I was funded as a single PI proposal by the NSF in the late 1990s to do what was called template oligomerization for the replication of precisely defined synthetic macromolecules. I tried to devise macromolecules that were not copied from nature, that were not a copy of nature's macromolecules, you could have an oligomer, monomers would bind to these, then they would couple, and then you could separate these two, and the mother and the daughter would now act each as a new mother for doing replication. We were killed by fidelity. We would get maybe 70% yield, and the other 30% just sits there. And that starts replicating itself and making a mess. And so it's just, the fidelity just wipes you out. So I do know something about this. All right, time makes abiogenesis less likely rather than more likely because molecules degrade. That's what I've said. So, quoting in that video.
So time does not solve the issue.
So this is an abbreviated example of one of Jim's favorite talking points, which is that long spans of time make abiogenesis less likely rather than more likely because biomolecules have a tendency to degrade. But there are some problems here. First, he is presuming that nature might synthesize one component of life one time and that's it. There's no reason to believe this. If conditions are allowing for some molecule to form or polymerize, then it can be doing that all the time. It polymerizes, then degrades, then polymerizes again.
All right, not everything goes back the way people think. Here's photoreactions that occur. UV light causes photo damage to DNA. So you have a DNA chain, you can get this coupling. Does this photochemical reaction just go back? You think so? Actually, time is an enormous problem. Let's see why. This is right off the Millipore Sigma website. This is a website where you buy DNA and you buy RNA. You buy it. They make it for you. or they isolate it from natural sources, or you can buy it. Let's see what they say. How do you store this stuff? Here's how they say. DNA oligonucleotides are relatively stable molecules. Okay, they're relatively stable. How stable are they? However, they require certain handling and storage techniques to ensure trouble-free experiments and maximum shelf life. The approximate shelf life of non-modified single-stranded DNA oligonucleotides with proper storage. So how long can they properly be stored? Well, if you're in a freezer at -20, stable for approximately 2 years, whether dry or in solution, being water or a tris EDTA buffer. Or if in the refrigerator at 4 degrees centigrade, they're stable for approximately 1 year. At room temperature, they're stable for approximately 3 to 6 months. On a hot day, they'll be stable for 1 to 2 months. You think time's a problem on a prebiotic Earth? Remember, when we're talking about prebiotic syntheses, we're talking about millions and billions of years. This is the twinkling of an eye in prebiotic terms of time. And this website says these are not stable. That's why I say time is a problem. Time is an enormous problem. Resuspension, storage, and working habits. When you have DNA that's dried out in your pools that like to dry out and reform, unless requested to ship in solution, all single-stranded DNA oligonucleotides ship dry and are ready for use upon resuspension, with the exception of thiol-modified sequences. Weak buffers such as TE, which is it's a tris buffer, it's a tris hydroxymethylamino-methane, with EDTA, which is ethylene diamine tetraacetic acid, and this captures ions like magnesium. So you have to put it in these sophisticated buffers in order to keep it stable. If T is unsuitable for N technique application, then sterile, nuclease-free water is the best choice. And again, you see the storage, how these things have to be stored. But the RNA world's favorite molecule is RNA. Well, how stable is RNA? Well, let's see what the Sigma Aldrich website has to say. Remember I told you that hydroxyl on RNA makes it a lot less stable than DNA doesn't have that. It's because that hydroxyl attacks that phosphate and it breaks. It says RNA is much more unstable than DNA due to its chemical structure. RNA is subject to autocatalysis as well as degradation by RNases. So there are enzymes. There are no enzymes here in prebiotic Earth to tear this up, but it's subject to autocatalysis. It self-decomposes. Does anyone really think that it just goes back to RNA? Does anyone really think that these things just go forward and back? Here's what it says. The 2-hydroxyl group of RNA can lead to autocatalytic degradation, which in turn, under the right condition, lowers the quality and usefulness of the oligonucleotide. For short-term storage, single-stranded RNA nucleotides should be stored in the tris EDTA buffer at -80 degrees centigrade. That's -112 degrees Fahrenheit. Where are you going to do that? You're going to synthesize this at room temperature or something so they can get these reactions to go, and then ship it on up to somewhere where it's -112 degrees Fahrenheit and store it there, and then use it within hours somewhere where it can hit a temperature where it can be used. I mean, this is crazy temperatures for storage of RNA. Okay, harnessing chemical energy for activation and joining of prebiotic building blocks. So here's an article that was written by John Sutherland, again, one of the masters in this. And he writes in this abstract, the joining of building blocks in aqueous solution from a common pool and enabled the progression of a system toward higher complexity, foreshadowing today's encapsulated peptide nucleotide acid system. So what he says here is that it is hard to join these in an aqueous system, really hard. And when you guys start throwing out reactions that all this happened in water, it's really hard. He himself says it. And so what he's trying to do here, he has come up with a chemistry that he feels could happen in water where you could start hooking amino acids onto these nucleotides. You hook amino acids onto nucleotides because amino acids do have to hook onto nucleotides. So he develops some chemistry that he thinks might be prebiotically relevant. And you need precise alignment guided by these homochiralities. So these all have to be chiral when it's used in nature. But here's what he comes up with. So what he does is he buys this material. He buys these nucleotides. Here's some nucleotides. He buys these. He buys the homochiral amino acid. So he buys this homochiral amino acid, and it's N-acetyl protected. So it's not the base amino acid, it's N-acetyl protected. Do you find these on a prebiotic earth? Do you find the homochiral ones, and are they N-acetyl protected? So then what he does is he reacts it with these methyl isonitriles. He says these store the energy to do these couplings. So here's the product that he goes to. Here's the joining of prebiotic building blocks driven by common activation. So he's joining these. Now if you look at what he joined, look at this. He goes from homochiral at that center. During the reaction, it all went racemic. Oh, what a shame. What a shame. He bought the homochiral building block, and it racemized. It got all, the stereocenter got all racemized. It's no longer homochiral. And he hooked it on here. And look, it got hooked on. But the NH, it didn't have the free amine. It had to be acetyl protected. Does that happen on prebiotic earth? Does it protect these groups? How did that happen? And even if it could, let's look at this chemistry here. Here's the compound that he made in what he presupposes could be a prebiotically relevant route. Now, let's look at time here. Let's look at time. So now we're going to track the synthesis of this. The synthesis of this goes up to the yield of 4.7%. It goes up to 4.7% yield when it was run at a pH of about 5. So the yield of 4.7% that was reached after 12 hours. So at 12 hours, he reached 4.7% yield. But then at 48 hours, it had declined to 2% yield. So 50% of what he made, the yield is bad, but anyway, 50% of what he made was gone after 2 days. You think time's a problem? I think so. Time is a problem. Because the very conditions that are used to make organic chemicals, compounds decompose under those very same conditions. Time is a problem in synthesis. Time causes synthetic degradation. Time is a problem. Under the very reactions that are used to form them, they decompose. And so what you have to do, the chemist has to go in there and pull it out, fish it out from those reaction conditions when it's optimized. Ribose-based systems like RNA are chemically very unstable, and it's not going back. Under most of the pHs, he got 0 yield. Under some of the pHs, he was able to get a yield, but then it declines. You think time's a problem? It is such a problem. That's why every slide in that video I didn't understand. It didn't make any sense to me. Every slide was wrong. I got nothing against the person that made that video. I'm just saying it was utter misinformation. Every slide was misinformation. It was said, so this is an abbreviated example of Jim's favorite talking point. And so again, you know, this tendency. Yeah, these things don't just polymerize again. We even have machines that can do this. So here's the summary. Jim is constantly talking about how we don't know how to make the 4 classes of biomolecules, which are nucleic acids, proteins, carbohydrates, and lipids.
This is ridiculous. Nucleic acid synthesis and protein synthesis are utterly trivial. It's so easy to do that we even figured out how to make machines that do it for us.
Yeah, this is really simple. But in these machines, remember, you get all your nucleotides from nature. What if you had to make those? And you don't buy those just like that. You buy them protected, already preloaded to be used in the machines. You don't use water as a solvent. Using purely organic solvents, using all human-made coupling agents. human-made deprotection agents. You're sweeping out all the impurities, and then after you're all done, you have to take those and put them through HPLC or this electrophoresis. You have to put them through purifications because even then it's a problem. How this happened on a prebiotic Earth, nobody knows. So in summary, for someone to trivialize the synthesis of nucleic acids and their oligomers is uninformed. When it was written at 651, these are utterly trivial to synthesize on that slide, which was taken from that video. It was unappreciated that it only looks easy to the novice because thousands of person years and billions of dollars have been poured into oligonucleotide syntheses. And the nucleotides, the building blocks of the building blocks, were purchased and obtained from biological sources. It is anything but trivial, as suggested. The nucleobases appended to the ribose or deoxyribose come from nature. Trying to make them with prebiotic restrictions can only be done when cheating via relay syntheses. And even with relay syntheses, it has only been shown in racemic form and often as gross mixtures of diastereomers on the ribose. And prebiotic mimics had overwhelming chemist input and conditions and sequences that would be hard to fathom on a prebiotic Earth. That's what you got to deal with on a prebiotic Earth. That's what it looked like. It's hard to fathom how those could have been made. It's hard to do these in a modern lab, using modern methods if you had to start from the chemicals on your shelf, if you couldn't just buy the sugars. But on a prebiotic Earth, using prebiotic relevant roots, we are clueless. I have never said it could not have been done. Never said that. Some people claim that. I never said it. As a scientist, I never say it could not have been done. I just say that as of today, we remain clueless. All right, well, if you want to see the next video we're going to take a little intermediate summary and just kind of catch up where we are. And then after that, we'll get into lipids. And if you want to subscribe, you can subscribe right here. And we'll send you an alert when the next video comes out. It's going to be soon. Thank you. Thanks for joining us. If you want to subscribe, just click right here, subscribe, and we'll give you a shout out when the next video in this series comes out.